Welcome to new video. In this lesson, we're going to cover improper integrals. We're going to learn what the improper integrals are and how to handle them step by step. And we're going to solve 10 full questions. Let's start. First of all, think of an integral from a to b. From a to b, f of x dx. And graphically, this will be a curve from a to b. Can we calculate this integral? Can we calculate the area under this curve? Yes, we can, because we know the boundaries and we can calculate the net area under this curve using our integration techniques. But what if our integral was something like this, starting from a going to positive infinity? Could we calculate the area under this curve? No, we can't, because we don't know our upper boundary. We don't have a finite value for upper boundary. It is going to infinity. How about here? Starting from negative infinity up to some value. Can we calculate the area under this curve? Still we cannot, because we don't know exactly what our lower boundary is. It's not a finite value. What if our integral is going from negative infinity to positive infinity? Can we calculate the area under this curve? Again, we cannot, because we don't know our lower and upper boundary exactly, and we don't have finite values here. How about this situation? We have integral from a to b, and we have vertical asymptote at b, which means there is a value here that makes the function undefined. Here we have a discontinuity. Can we calculate the area under this curve from a to b? Again, we cannot calculate the area under this curve from a to b because b is not our upper boundary, because it is the value that makes the function undefined. How about here? From a to b, can we calculate the area under this curve? At a, we have vertical asymptote. Again, we have this continuity here. A is not exactly our lower boundary because the function cannot get that value. How about this situation? We have integral from a to b, but we have this continuity in between at value c. Can we calculate the area under this curve? Let's see. From here to here, it seems there is no problem, but from here to here, we have a problem, that discontinuity. And again, we have another problem here. So we cannot calculate this integral as well, because c is not the value in the function. So these type of integrals, that's 6 cases, are called improper integrals. So how are we going to handle these type of integrals? What's going to be our approach to calculate these integrals? We're going to see that at the next page more formally, but graphically here, let me explain a bit. So from a to positive infinity, we cannot calculate this integral. But from a to t value, some value here, I can calculate the area from a to t, right? And if I make t value approach to positive infinity, I can calculate this integral. So how can I make t value approach to positive infinity? What comes to your mind? In mathematics, what technique can we apply? Limits. So we're going to use limits to calculate this integral. We're going to make t value approach to positive infinity using limits, and from a to positive infinity, we will calculate this integral. We will use the same logic here. We will pick up some t value, and from t to a, we will calculate the integral and make t value approach to negative infinity. Here, we will do one extra step. We will split this integral into two integrals. From negative infinity to some t value, we will cut it somewhere here, any value you would like, plus from t to positive infinity. So we will split this integral into two integrals and then apply these techniques we used here. How about here? From a to b. So I can pick up a value very close to b. So how can I approach b? From left or right? I have to approach b from the left. So from a to b, I will approach the b value from the left. And here, this is our lower boundary, which is the vertical asymptote. From a to b, I can calculate this integral using limits. I can pick a value very close to a from the right. I can pick up a value very close to b from the left. And here, I have to split this into two integrals at the vertical asymptote. So from a to b, f of x dx can be rewritten as from a to c, f of x dx plus from c to b, f of x dx. And I can pick a value very close to c here, and I have to approach c from the left here, and I have to approach c from the right here. So we're going to use this logic. More formally, improper integrals have two types, type 1 and type 2. Let's see what they are. Type 1 is the infinite interval. So what cases do we have? In infinite interval, we have three cases. Either the upper boundary is going to infinity. In case 2, the lower boundary is going to negative infinity. Or in case 3, either boundaries go to infinity. In type 2, we have discontinuous interval. What do we mean by discontinuous interval? We have vertical asymptote at some value that makes the function undefined. Let's see the cases. In case 1, we have upper boundary vertical asymptote. At x equals to 3, the function is undefined because 3 minus 3 is 0, 1 divided by 0 is undefined. So this function has vertical asymptote at x equals to 3, which is our upper boundary. In case 2, we have vertical asymptote at the lower boundary. Here at x equals to 1, the function is undefined and there is a vertical asymptote. And in case 3, we have a vertical asymptote within the boundaries, in between some value. Here at x equals to 2, the function has a vertical asymptote. Now let's see the steps for solving improper integrals. If we have case 3 of either type 1 or type 2, first we start with splitting the integral into two integrals. Here it is illustrated. If we have boundaries going from negative infinity to positive infinity, we have to split this integral into two, from any value you would like. And if we have here vertical asymptote within the boundaries, so you have to split this integral into two integrals from the vertical asymptote. So here we have vertical asymptote at x equals to 2. So we have to split this integral from 1 to 2, where there is vertical asymptote, and from 2 to 3, which is to upper boundary. In general, steps are like this. First, we convert integral to limit. How are we doing that? So it is illustrated here, the 6 cases. Let's see how they are. So if we have from a to positive infinity, which is the upper boundary is going to infinity, then we pick t value and make it approach to infinity and calculate the integral from a to t of f of x. If we have negative infinity to a case, which is lower boundary is going to infinity, then we pick t value and make it approach to negative infinity, and we calculate the integral from t to a. If we have both boundaries going to infinity, then first we have to split this integral into 2 integrals. And we can split this integral from value a and pick t value and approach it negative infinity and calculate it from t to a value, plus we pick t value, which is approaching to positive infinity this time, and calculate the integral from a to t. If we have upper boundary as our vertical asymptote, then we convert this integral into limit like this. Limit as t approaching to upper boundary, here 3, from the left side, and we calculate the integral from 1 to t. If you have upper boundary as your vertical asymptote, then you approach your limit from the left, because it is the only way to approach the upper boundary from the left. If you have lower boundary as your vertical asymptote, then you have to approach it from the right, because there is only one way to approach it. So here, when we convert this lower boundary into limit, which is 1, then limit as t is approaching to 1 from the right side here, then the integral of t to 3. If we have vertical asymptote in between, then we have to split this integral into 2 from the vertical asymptote. So here our vertical asymptote is at 2. So from 1 to 2 is our first integral, and 2 to 3 is our second integral. And the first part of the integral is approaching to 2, approaching to our vertical asymptote from the left. And the second integral is approaching the vertical asymptote from the right. Graphically, it is as on our page 1. Here, we have a vertical asymptote between the boundaries, and the first part of the integral we're approaching to boundary from the left, and at the second integral we're approaching to vertical asymptote from the right. So after we converted integral into limit, then we evaluate the integral value on our boundaries. And finally, as our step 3, we find the limit as t is approaching to either negative infinity or positive infinity or finite value. So as a result, if we get negative infinity, positive infinity, or if the limit does not exist, then we call it divergent. If we get a finite value, a number, as an answer, so it is called convergent. Now we're going to solve 10 questions below, and we will see each case and situation very well. Here is the first question. In this question, what makes our integral improper integral? Let's observe. Our integral is going from 2 to infinity. So our upper boundary is infinity. So this is improper integral, type 1. So let's start solving step by step. So step 1. What was our first step? Our first step was to convert integral into limit. So convert to limit. Convert to limit. So let's convert integral into limit. So our integral from 2 to infinity, 1 over x dx, becomes limit as t is approaching to infinity, integral from 2 to t of 1 over x dx. So now our integral is not improper anymore because we can calculate this. Step 2. Step 2 is to calculate the integral. Calculate calculate the integral. So let's see. So our integral is limit as t is approaching to infinity, integral from 2 to t 1 over x dx equals to limit as t is approaching to infinity. Okay, so what is the antiderivative of 1 over x? 1 over x is our ln x. This is our classical integral evaluated at 2 to t. Now we're going to evaluate ln of x from 2 to t. So it's going to be limit as t is approaching to infinity, ln of t minus ln of 2. So our second step is also completed. Now our step 3, what is our step 3? Step 3 is to calculate limit. So calculate limit. Okay, so if you plug it in here, infinity, it's going to be ln of infinity minus ln of 2. So what is ln of infinity? You need to know the graph of ln, which is going to be very helpful. So as x is going to infinity, the function ln is going to infinity as well. So if we plug infinity here, a large number, ln will be positive. And ln of 2 is some value. It is insignificant because infinity minus any value is still infinity. So our answer is infinity. So since we get answer infinity, our integral is divergent. This is also useful to know p integral. If we have integral from 1 to infinity, 1 over x to the p, If your p-value is greater than 1, then your integral is convergent. If your p-value is equal to 1 or less than 1, then your integral is divergent. So this key is also an important point to know. For example, if you had integral from 1 to infinity, 1 over x squared, what would you say about it? Is it divergent or convergent? What is our p-value here? Our p-value is 2, and p is greater than 1 because 2 is greater than 1. So this integral would be convergent. If we had 1 to infinity, 1 over x would be divergent because our p-value is 1. Let's go to second question. In question 2, why is our integral improper? Our integral is improper because our lower boundary is going to negative infinity. So type 1 kind of improper. So let's start. So what is our first step? Again, our first step is converting integral to limit. So convert integral to limit. Okay, so our integral from negative infinity to 1 e to the x dx becomes limit as t is approaching to negative infinity. Be careful, not positive infinity. Integral from t to 1 e to the x dx. So we completed our step 1. We completely converted our integral into limit. Now we're going to evaluate this integral. So step 2. Step 2 is calculate integral. So our integral, which is limit as t is approaching to negative infinity, integral from t to 1 e to the x dx, becomes limit as t is approaching to negative infinity. So what is the antiderivative of e to the x? Antiderivative of e to the x is again e to the x. So e to the x evaluated at t to 1. And it becomes limit as t is approaching to negative infinity. So we have to plug it in upper boundary and lower boundary here. E to the 1 minus e to the t. And here, if we clean up limit as t is approaching to negative infinity, e to the 1 is e minus e to the t is t. And here, if we plug it in our values, our limit values, e is e minus e to the negative infinity. So what is e to the negative infinity? If you know the graph of e to the x, it will be very helpful. So as x is going to negative infinity, e to the x is approaching to 0. So this is 0. Or if you don't know the graph by heart, you could do like this. E to the negative infinity, you can convert it into 1 over e to the positive infinity. E is some number, and number to the positive infinity. So 1 over e to the some positive infinity is infinity, and 1 divided by infinity is 0, because our value is approaching to 0. So this is e, this is 0, e minus 0 is e. So the answer of this integral is e. So e is some number, Euler's number, irrational number, and some finite value. So our integral is convergent. Convergent. Okay, let's go to question number 3. Here is our question number 3. Okay, what makes our integral improper here? It is very clear that our lower boundary and upper boundary is going to infinity. So this integral is improper type 1, case 3. Since our lower boundary and upper boundary is going to infinity, before we start the steps, we're going to split this integral into 2. Let's do that. So how are we going to split that integral? From what value? So it doesn't matter what value you pick, but I'm going to pick it 0, because 0 will be meaningful when I take the antiderivative of this. So I split this integral into integral from negative infinity to 0. Again, that value is completely up to you. 1 over 1 plus x squared dx plus from 0 to infinity the same function 1 plus x squared dx. Now we split this integral into 2 integrals. Now we can start the steps. Step 1. What was our step 1? Step 1 is to convert integral to limit. So we're going to convert integral to limit. Okay, let's convert each integral into limit one by one. So our original integral, which is negative infinity to positive infinity, 1 over 1 plus x squared dx, becomes, so we're converting the first integral here now, limit as t is approaching to negative infinity, integral from t to 0 of 1 over 1 plus x squared dx plus the limit as t is approaching to positive infinity, integral from 0 to t 1 over 1 plus x squared dx. X squared dx. So our step 1 is completed. Let's go to step 2. What is our step 2? Step 2 is to calculate the integral. So step 2 is to calculate the integral. So limit as t is approaching to negative infinity. So what is the antiderivative of 1 over 1 plus x squared? This is our arctangent of x. If you're familiar with the inverse trigonometric functions, it's going to be very helpful. So you can see the pattern here. This is tangent inverse. So it's going to be arctangent of x evaluated at t to 0 plus our second integral will be limit as t is approaching to positive infinity. Again, our antiderivative is arctangent of x. Arctangent of x evaluated at 0 to t. Let's continue. So limit as t is approaching to negative infinity. So we're gonna plug it in our upper and lower boundary, f of b minus f of a, arctangent of 0 minus arctangent of t. Plus limit as t is approaching to positive infinity. Again, we're going to plug it in our upper boundary and lower boundary, f of b minus f of a. So it's going to be, let me write tangent inverse so it's going to be more compact. Tangent inverse or arctangent, the same terminology. So tangent inverse of t minus tangent inverse of 0. Okay, here our second key. If you know the graph of tangent inverse, it's going to be very helpful. Our tangent inverse has the boundaries. Upper boundary is pi over 2. We have a horizontal asymptote here. And negative pi over 2 is our another horizontal asymptote, lower boundary. And tangent inverse goes from negative infinity to positive infinity. And it will be very helpful to find the arctangent values. So here arctangent 0 is our origin, which is 0. So our tangent inverse 0 is again 0. So this is 0, this is 0. And if we plug it in our limit here, this will be negative infinity, and this will be positive infinity. So arctangent of negative infinity, as x goes to negative infinity, our arctangent goes to negative pi over 2. So negative pi over 2 plus, and as our x is going to infinity and our tangent function is going to pi over 2 and minus 0. Let me put two more values on tangent so it's going to be very helpful. Let me use pink, which is more notable. So at 1, positive 1, and at negative 1. So tangent value at positive 1 is pi over 4. This is important value for arctangent. And at x equals to negative 1, our arctangent value is negative pi over 4. So if you know this graph, you automatically know 1, 2, 3, 4, 5 values of arctangent. Okay, let's continue our evaluation. So this is negative pi over 2, which will be pi over 2 plus pi over 2. So our integral will be pi over 2 plus pi over 2 is pi. So our answer is pi, and pi is a finite number, finite value. So our integral is convergent. Okay, let's go to next question, question number 4. Okay, in question number 4, what makes our integral improper? Let's observe. We don't have infinity as our boundaries. So let's check if we have vertical asymptote. Okay, what makes this function undefined? X minus 3 equals to 0 if we solve for x. So 3 is the value that the function cannot get at denominator. So we have vertical asymptote at x equals to 3. So 3 is our upper boundary. So this is type 2 improper integral and our case 1. So we're going to convert this integral into limit as our first step. Let's do that. So limit as t is approaching to 3 from the left. Why? Because this is our upper boundary, and whenever you have upper boundary, you're approaching from the left. If you have vertical asymptote on the lower boundary, you're approaching from the right. So limit as t is approaching to 3 from the left, integral from 1 to t, 1 over x minus 3 dx. Our step 1 is done. So let's go to step 2. What was step 2? Step 2 is to calculate this integral. Limit as t is approaching to 3 from the left. So what is the antiderivative of this function? It's going to be ln of x minus 3. If you can't tell directly by heart, you can use u substitution here. Your u will be x minus 3 and your du will be your dx, and eventually you're gonna have 1 over u, which will be ln of u, and then if you bring u back, you're gonna get ln of x minus 3. So ln of x minus 3 evaluated at 1 to t. So let's plug it in our upper and lower boundaries. So limit as t is approaching to 3 from the left, ln of t minus 3, which is our f of b, minus ln of 1 minus 3 in absolute value. Okay, equals to. So let's clean up this. Limit as t is approaching to 3 from the left, ln of absolute value t minus 3, which is our f of b, and this is f of a, minus ln of 1 minus 3 is negative 2. Here, negative 2, the absolute value executes it as ln of 2 positive 2. We have negative sign here. We have ln of t minus 3 and limit as t is approaching to 3 from the left. So what happens if I plug it in here 3? So 3 approaching from the left is slightly smaller than 3. So here we're approaching to 0 from the left, minus ln of 2. And absolute value execute it as ln approaching to 0 from the right, because negative value will be positive, minus ln of 2. Again, if you know the graph of ln, it's going to be very helpful. Let me show you here how ln's graph is behaving. Okay, let's say this is our ln function, ln of x. So we're approaching to 0. This is 0, our origin. We're approaching to 0 from the right. Let me pick good color to show. So we're approaching to 0, I'm sorry, from the right. So as we approach 0 from the right, where do we go? we're going to negative infinity, right? So this value will be negative infinity. And again, ln 2 is some value. It doesn't matter what it is because it's insignificant comparing to infinity. So negative infinity minus any value is still negative infinity. So our answer is negative infinity. And if we get negative infinity, positive infinity, or if the limit does not exist, what do we call it? We call it divergent. So our integral in question number 4 is divergent. Let's go to question number 5. Here is question number 5. So in this question, what makes our integral improper? We don't have infinite boundaries, but we have a value that makes the function undefined. At x equals to 1, our function is undefined. Because 1 minus 1 is 0, 1 divided by 0 is undefined. So this is type 2 discontinuity, improper integral. So let's start step 1. Step 1 is converting integral into limit. So we have discontinuity, or we have vertical asymptote at the lower boundary. As you can see here, we're going to approach the lower boundary from the right. So limit as t is approaching to 1, which is our vertical asymptote, from the right, integral from t to 3, 1 over x minus 1 dx. So step 1 is completed. We converted integral to limit. Now we're going to start step 2. What is step 2? Calculating this integral. So limit as t is approaching to 1 from the right, integral t to 3, 1 over x minus 1 dx equals to limit as t is approaching to 1 from the right side. So what is the antiderivative of 1 over x minus 1? It is ln x minus 1 in absolute value. Again, if you can't tell directly, you can use u substitution here, and your u will be x minus 1, your du will be dx, and your integral will be 1 over u, which is ln of u, and then when you bring u back, it's going to be ln of x minus 1. Evaluated at t to 3. So we're going to plug it in our f of p minus f of a. So limit as t is approaching to 1 from the right, ln of, instead of x, we're going to use 3, which is our upper boundary, 3 minus 1, minus ln t minus 1. Okay, so let's clean this up. So limit as t is approaching to 1 from the right, 3 minus 1 is ln of 2, absolute value, minus ln of t minus 1. Now we can substitute our limit value, direct substitution. So ln of 2 minus, okay, if we approach 1 from the right, this is slightly bigger than 1. So this value is slightly bigger than 1. So here we approach 0 from the right, because a number slightly bigger than 1 minus 1 will be a value which is approaching to 0 from the right. And Again, if you know the graph of ln, it's going to be very helpful. So let's sketch it roughly. ln is like this. Only at 1 it is 0. So as you approach to 0 from the right, your ln value is going to negative infinity. So this is equal to negative infinity. We have ln of 2 minus infinity. So this will be equal to, ln of 2 is insignificant value comparing to negative infinity here. So any value minus infinity, so negative infinity will be positive infinity. So here our answer is positive infinity. So our integral is divergent. Okay, let's go to example 6. Okay, in example 6, what makes our integral improper? Let's check. We don't have boundaries going to infinity, but we have a value that makes the function undefined. We have discontinuity type of improper integral. So at x equals to 2, x cannot be 2, otherwise our function will be undefined. We have vertical asymptote. So at x equals to 2, we have vertical asymptote. So this is case 3, type 2, case 3. Before we start the steps, we're going to split this integral into two integrals. So equals to, our first integral will be from 1 to 2. Why from 1 to 2? Because we have vertical asymptote at 2. Our lower boundary is 1. Our upper boundary is 3. We have vertical asymptote at 2. So from 1 to 2 will be our first integral, and from 2 to 3 will be our second integral. So from 1 to 2, 1 over x minus 2 dx is our first integral, plus from 2 to 3, 1 over x minus 2 dx is our second integral. Now we can start converting this into limit. So our first integral will be limit as t is approaching to our vertical asymptote 2. From where? From right or left? We're approaching to vertical asymptote from the left, as you can see visually here at the first integral. So integral from 1 to t, we cannot use 2 anymore because it's our vertical asymptote. 1 over x minus 2 dx plus limit as t is approaching to 2 from the right. So we're approaching 2 from the right at the second integral. So integral t to 3, because we are removing our vertical asymptote, 1 over x minus 2 dx. Now we're going to calculate these integrals separately. Okay, so the first integral, limit as t is approaching to t is approaching to 2 from the left. So what is the antiderivative of 1 over x minus 2? It's going to be ln of absolute value x minus 2. Again, if you can't tell directly, you can use u substitution here. Evaluated at 1 to t plus limit as t is approaching to 2 from the right side. And again, antiderivative of this function is ln of x minus 2 evaluated from t to 3. Now we're going to plug it in t and 1. We're going to plug in our b, f of b and f of a values. So limit as t is approaching to 2 from the left, ln of, instead of x, we're going to plug in t minus 2 minus ln of 1 minus 2. We have plus here. All we did up to here was this integral, and now we're going to do this integral. The limit as t is approaching to 2 from the right, ln of, instead of x, we're going to plug in our upper boundary, 3 minus 2, minus ln of now lower boundary, t minus 2. Alright, so let's see. If we clean up, this is ln t minus 2 minus ln 1 minus 2 is negative 1 plus this is going to be ln of 3 minus 2 is 1 minus ln, this is n, t minus 2. Let's plug in our limit as well. Limit as t is approaching to 2 from the right, and limit as t is approaching to 2 from the left. Now we can plug in our limit values directly, direct substitution. If we plug in t value here, we will get ln of 0 to the left. Why? Because if we plug in here 2 from the left, which is going to be slightly smaller number than 2, which is we're approaching to 0 from the left. And ln of negative 1 will be ln of 1. Absolute value makes it ln of 1, and it's going to be 0. ln of 1 is 0. So we can ignore that. Plus ln of 1 is 0 again. This value is 0. If we plug in here 2 approaching from the right, we're going to get ln of 0 approaching from the right, because we will have slightly bigger than 2. So we're going to have this. And absolute value again makes this positive. So ln of 0 approaching from the right. If you know the graph of ln, again, it's going to be very helpful. ln behaves like this. If you approach to 0 from the right, your function is going to negative infinity. So this is going to be negative infinity, negative, and this is going to be again negative infinity. So negative infinity, negative, negative infinity. So this type of situation is also undefined. If you come across with this answer, you have to go a few steps back to limit and apply L'Hopital's rule. Okay, so we need to apply L'Hopital's rule. But here we're not going to apply L'Hopital's rule because I just wanted to show you, if you come across this type of answers, we have two other practical solutions for this question. We're gonna do that for this question. I will apply L'Hopital's rule at another question. So let's clean up a few steps back. So let's go to here. let's not plug in our limit value. Okay, so when you split your integral into two integrals like here, so this is our first integral and this is our second integral. So what is the first integral? It is ln of 0 approaching from the left. Absolute value makes it ln 0 approaching from the right, and it makes the answer negative infinity, as in here. So if you have two integrals and if one of them is diverging, definitely the second one is also diverging. So this is another key practice. Okay, so let's formulate it like this. If we have, let's say, integral of f of x, let's say from a to b, or it could be negative infinity to positive infinity, or some value to another value, which is undefined. So if we have two integrals here, and if one of them is diverging, the other one is also diverging. So this is a certain rule. So you can add this as your second key in this question. So this is the one solution of this question. So we can say that this is diverging because one of the integrals is diverging. Divergent. Second way of solving this question is graphically, what is 1 over x minus 2? This is a very famous graph shifted. What is the parent function here? 1 over x. So 1 over x is shifted 2 units to the right. And we have vertical asymptote at x equals to 2. So let's draw the vertical asymptote first. And we know that our parent function is 1 over x. So 1 over x is behaving like this. Like this. So at x equals to 2, how is our function behaving? As you can see here, it is diverging to negative infinity and positive infinity. So our function is diverging here. So you can graphically see it, what we mean here. So the first integral is going to negative infinity, the second integral is going to infinity, and eventually it is diverging. Let's go to next question, question number 7. So what makes our integral improper? Let's observe. We don't have infinite boundaries, but we have a value that makes the function undefined. We have vertical asymptote at x equals to 1. And the value 1 makes this function undefined because it makes the denominator 0. So this is type 2, discontinuity type of improper integral. Okay, let's start with step 1. Step 1 is to convert integral to limit. So limit as t is approaching to 1 from the left side, because we're approaching to our upper boundary, and we can approach to upper boundary from the left side. Integral from 0 to t for x divided by radical 1 minus x to the 4th dx. Our step 1 is completed. So we're going to go to step 2. What is step 2? Step 2 is to calculate this integral. Here we have to see the pattern. This is the pattern of arcsine. What is arcsine? I have given you as a key here. 1 over radical 1 minus x squared is our arcsine of x. So we're going to make this function look like this. Let's rearrange. So that is equal to limit as t is approaching to 1 from the left side, integral from 0 to t. So 2 times 2x is 4x divided by square root of 1 minus x to the 4th dx. Here we're going to do normal u substitution. So what is our u? How can we define the u? Here is the pattern. We have to make it look like arcsine. So if we pick u as x squared, our du will be 2x dx. That will cancel out the top. So du will be 2x dx. And if you solve for dx here, it's going to be du over 2x. So let's write in terms of u now. That is equal to limit as t is approaching to 1 from the left side, integral from 0 to t, 2 times 2x divided by radical 1 minus u squared. X to the 4th is u squared squared, so it's going to be u squared. And instead of dx, we're going to write du over 2x. du over 2x. 2x's cancel out, so we're going to have here arcsine. So let's rewrite that. Limit as t is approaching to 1 from the left side, we can pull this constant to the front. 2 times integral of 0 from 0 to t, 1 over 1 minus u squared du. Now this looks like exactly our arcsine. So this is exactly what we needed. Okay, so let's convert it. Limit as t is approaching to 1 from the left side. So antiderivative of this function is arcsine of u. Arcsine of u evaluated at 0 to t. Now we're going to calculate arcsine of u from 0 to t. So we're going to plug in our upper boundary minus lower boundary, f of b minus f of a. And we can bring u back here. So limit, and actually this is 2 arcsine because we have 2 in front. Okay, limit as t is approaching to 1 from the left side, 2 arcsine of u. Instead of u, we're going to write x squared because that was our u from the u substitution, minus 2 arcsine okay, so let's plug it in directly. Okay, 2 arcsine x squared. Let's do like this first. Okay, at the first f of b, our arcsine, instead of t, we're going to plug in our upper boundary, which is t squared, minus 2 arcsine 0 squared, it is 0, directly 0. And we have to bring our limit here, limit as t is approaching to negative 1, sorry, 1 from the left side. Okay, So here it's very useful to know the graph of arcsine. So graph of arcsine is like this. The domain is from -1 to +1, and the range is pi over 2 upper boundary, -pi over 2 is the lower boundary. And our graph is like this. This is how our arcsine is. This is sine inverse of x, or arcsine x. So here we can automatically tell arcsine is 0, arcsine of 1 is pi over 2, arcsine of -1 is -pi over 2. So if we plug in our limit direct substitution, it's going to be 2 arcsine 1 squared is 1 minus 2 arcsine 0. So arcsine of 1. Arcsine of 1 is, if you look at the graph, it's pi over 2. Two times 2 pi over 2 minus 2 times arcsine 0 is 0, 2 times 0. So this whole expression here is 0, 2 times 0 is 0, and 2 times pi over 2 is pi. So the answer for this question is pi. And pi is a finite value, so this integral is convergent. Okay, let's go to the next question. Question number 8. In this question, what makes our integral improper? Let's observe. We don't have infinite boundaries. Let's check if there is any value that makes the function undefined. Here our function is ln of x, and ln of x cannot get the value of 0. Ln x, or ln of 0, is undefined. So at x equals to 0, we have vertical asymptote. And if you think of graph of ln, you can see that we have vertical asymptote at 0. ln can never reach 0, but approaches. Okay, this is ln of x. So we're going to convert our integral to limit as our first step. So limit as t is approaching to, where is our vertical asymptote? 0. And it is our lower boundary, so we're approaching to 0 from the right side. Limit as t is approaching to 0 from the right, t to 1, integral t to 1 ln of x dx. Now our second step is to calculate this integral. Limit as t is approaching to 0 from the right, integral t to 1 ln of x dx equals to limit as t is approaching to 0 from the right. So what is ln of x? What is the integration of ln of x? So this is one of our classical integrations, classical integrals. So you need to know ln of x by heart. Integral of ln of x dx equals to x ln x minus x plus c. If you don't know it by heart, you're going to apply here integration by parts. And your u will be your ln x, and your dv will be 1. And your du will be 1 over x dx. And your v will be the antiderivative of 1 with respect to x. So you can continue here integration by parts, applying the formula u times v minus integral of v du, and you can get this result, or you can memorize this by heart, because you need to know the integral of ln of x, tangent x, secant x, secant cube of x are the classical integrals that you need to know by heart. In my other videos, you can see it in detail. So no need to reinvent the tire now. Let's continue using our key here. Okay, so let's accept it as it is. So our limit, our integral turns to limit as t is approaching to 0 from the right side. So the antiderivative of this function is x ln x minus x evaluated from t to 1. Now we're going to insert our upper boundary and lower boundary. So f of b minus f of a. So our first function will be 1 times ln x, 1. So 1 ln 1 minus 1 is our f of b minus, so t ln t, t ln of t minus t is our f of a. But there, let's make a little bit space, as limit as t is approaching to 0 from the right side. Here ln of 1 is 0, and 0 times 1 is 0. 0 minus 1 is negative 1. So this whole parenthesis is negative 1 minus t ln t. So if we do direct substitution, it's going to be 0 times ln of 0 approaching from the right side minus 0. So again, if you look at the ln function, if you approach to 0 from the right side, it's going to be negative infinity. And we have 0 here. 0 times negative infinity minus 0. So this is indeterminate form. 0 times negative infinity is one of the indeterminate forms. Okay, indeterminate form. So we need to remove this situation. So we have to apply L'Hopital's rule here. So only for this part, we're going to apply L'Hopital's rule. Okay, L'Hopital. But to be able to apply L'Hopital's rule, again, another key, we have to have form of infinity over infinity, positive or negative, or 0 over 0, indeterminate form. So we're going to manipulate this function. So let's do L'Hopital here. So limit as t is approaching to 0 from the right side, t ln t. So this is the part that we are applying L'Hopital. Why? Because this multiplication causes indeterminate form here. Okay, so we are going to rewrite this because we need to get either infinity over infinity or 0 over 0 to accommodate L'Hopital. So how can we rewrite this function t ln t? We can rewrite it as ln t divided by 1 over t, which will be equal to t times ln t. So limit as t is approaching to 0 from the right side, ln t divided by 1 over t, which is basically t times ln t. Here, if we plug in our limit direct substitution, it's going to be ln approaching to 0 from the right, 1 over 0 approaching to right. So our numerator will be negative infinity, because ln approaching to 0 from the right is negative infinity, and 1 divided by a number which is getting smaller and smaller, it's going to be positive infinity. So we have the form to apply L'Hopital's now. Okay, so infinity over infinity justifies us to use the L'Hopital. So what was L'Hopital? We're going to take the derivative of this function, the numerator and denominator. So what is the derivative of ln t? So let's rewrite here limit as t is approaching to 0 from the right side. So what's the derivative of ln t? The derivative of ln t is 1 over t divided by, what is the derivative of 1 over t? If you apply here power rule, this is t to the negative 1. The derivative of 1 over t is negative 1 over t squared. Actually, this is also one of the situations that you need to know. So the derivative of 1 over x is negative 1 over x squared. Okay, so here we do basic algebra, keep change flip, 1 over t times negative t squared over 1, so it gives us negative t. And here we have negative t, and if we plug it in 0, our limit, if we plug in our limit, we get 0. So this part is 0, and 0 minus is 0. So our answer will be negative 1 minus 0, so our answer is negative 1. So this integral equals to negative 1. And it is a finite value, so we can tell it's convergent. It converges to negative 1. Okay, let's go to next question. Question number 9. So what makes this integral improper? As you can see here, our upper boundary is going to infinity. So this is type 1, infinite boundary type of improper integral. So let's start with our step 1. What was step 1? Step 1 was to convert this integral to limit. So limit as t is approaching to infinity, integral from 0 to t 1 over 1 plus x squared times 1 plus arctangent of x dx. So here you can see the pattern. The derivative of arctangent of x is 1 over 1 plus x squared. So arctangent of x can be our u, and this is going to be our du. So let's do that. But let's write the key here before that. Let me write the key for u. The derivative of arctangent dx of tangent inverse of x equals to 1 over 1 plus x squared. Okay, so here we're going to do normal u substitution, and our u will be 1 plus 1 plus arctangent. I'm going to write as tangent inverse, so it's going to be compact. 1 plus tangent inverse of x. So our du will be what? The derivative of this. The derivative of that is 1 over 1 plus x squared dx. And if you solve for dx here, dx equals to, so this is 1, dx equals to 1 plus x squared times du. So if we write in terms of u, we're going to get this. Limit as t is approaching to positive infinity, integral from 0 to t 1 over 1 plus x squared. In terms of 1 plus arctangent of x, we're going to write u, and instead of the x, we're going to write 1 plus x squared times du. And here 1 plus x squared cancels out, so our integral will be 1 over u. So limit as t is approaching to infinity, integral from 0 to t 1 over u du. So very good. We know what 1 over u is. So integral of 1 over u is what? ln u plus c. So this can be our another key here, or ln 1 over x is ln x. Okay, so limit as t is approaching to infinity, so ln of u evaluated at 0 to t. And here, instead of u, we're going to bring our u. What was u? It is 1 plus arctangent of x. This is 1. So let's evaluate this integral. Limit as t is approaching to positive infinity. So f of b minus f of a. F of b is ln of 1 plus arctangent t is our f of b minus ln of 1 plus arctangent of the lower boundary 0. Again, it's going to be advantage to know the graph of arctangent very well. Arctangent has the horizontal asymptote here as the upper boundary and the lower boundary here. And from negative infinity to positive infinity, the upper boundary is pi over 2. The lower boundary is negative pi over 2. Arctangent 0 is 0. And arctangent of 1 is pi over 4. Arctangent of negative 1 is negative pi over 4. So those are the values that you need to know, or you can memorize this graph. Okay, so let's put the values limit as t is approaching to 0, positive infinity. So this is, if we plug it in here, it's going to be ln of 1 plus arctangent of positive infinity minus ln of 1 plus arctangent of 0. Here, arctangent, as x is going to infinity, arctangent is approaches to pi over 2. And this is going to be 1 plus pi over 2 in absolute value, ln in absolute value, minus ln of 1, arctangent of 0 is 0, so 1 plus 0 is 1, and ln of 1 is 0, we know that. It is a famous value. Okay, so this is the answer. Ln 1 plus pi over 2 minus 0 is still ln 1 plus pi over 2. So this is the answer. And ln 1 plus pi over 2 is a finite value, so our function, our integral, is convergent. Okay, let's go to final question now. What makes this integral improper? As you can see, our lower boundary and upper boundary is going to infinity. So this is type 1 infinite boundary improper integral. And this is case 3 because our lower boundary and upper boundary both going to infinity. So first we're going to split this integral into two integrals and then start applying the steps. But we have to be careful here that we have absolute value sign. So we need to eliminate absolute value sign. How are we going to do that? We know that absolute value of x is negative x between negative infinity to 0. And we know that absolute value of x is positive x from 0 to infinity. Knowing this property, knowing the absolute value of x, we can eliminate the absolute value sign here. So we can split this integral into two integrals from negative infinity to 0 plus from 0 to positive infinity. So from negative infinity to 0, we know that our absolute value of x is negative x. So e to the negative sign is in front. Instead of absolute value of x, we're going to write negative x dx. And from 0 to infinity, we have negative sign in front. And instead of absolute value of x, we're going to write positive x dx. After splitting this integral into two integrals, we can start our steps. So step 1. What was step 1? Step 1 was converting limit, integral to limit. So our first integral will be limit as t is approaching to negative infinity, integral from t to 0, e to the negative x, which we can directly write e to the x dx, plus limit as t is approaching to positive infinity, e to the negative x dx. So our step 1 is completed. Let's go to step 2. What is step 2? Step 2 is to calculate the integral. Limit as t is approaching to negative infinity. So what is the antiderivative of e to the x? It is e to the x again, evaluated at t to 0. Plus, our second integral will be limit as t is approaching to positive infinity. So we have here integral sign, we forgot, from 0 to t. So what is the antiderivative of e to the negative x? It's going to be negative e to the negative x, evaluated from 0 to t. And now we're going to plug in our upper and lower boundary, f of b minus f of a. So our first integral will be limit as t is approaching to negative infinity. So our upper boundary is 0, e to the 0 minus e to the t. This is our first integral, plus our second integral is limit as t is approaching to positive infinity. Our upper boundary is t, negative e to the negative t, minus our lower boundary is 0, negative e to the negative 0 is 0, just 0. Okay, let's clean up. E to the 0 is 1, e to the 0 is 1. Okay. So knowing the graph of e to the x will be very helpful. So e to the x is a function, exponential function, something like this, e to the x. We know that e to the x is 0 as x is approaching to negative infinity. As we go to the negative infinity, the function is approaching to 0. As we're going to positive infinity, e to the x is going to positive infinity. So if we plug in our limit here, it's going to be e to the negative infinity, and e to the negative infinity is 0, and negative 0 is 0. So this is our first integral, plus if we plug in our integral limit here, it's going to be positive infinity instead of t, and negative infinity. E to the negative infinity is approaching to 0, and negative 0 is still 0. And e to the 0 is 1, anything to the 0 is 1, and it will be negative 1, and negative 1 will be positive 1. So we will have 1 here, and we will get 1 here, and the answer is 2. So 2 is a finite value, so our integral e to the negative absolute value of x from negative infinity to positive infinity converges to 2. So this is convergent. Whenever you have finite value, your integral is convergent. whenever you have positive infinity or negative infinity, or the limit is undefined, the function is undefined, then your integral is diverges. So this is the end of the video. Thank you for watching. I hope you liked the video. See you at the next video.